All right. Hello, everyone. Thank you for joining us today for explaining the Postgres query optimization or optimizer. My name is Vibhor Kumar. I'm a global vice president at EDB. I lead a team of highly skilled engineers across the world, ensuring that clients' Postgres database systems are optimized for maximum performance and scalability. With me, we have a Bruce Momjian. He's our today's speaker. He needs no introduction as he's a prominent figure in the Postgres and has contributed significantly to Postgres. PostgreSQL is a powerful and open source relational database, as you know. Bruce is a co-founder of the PostgreSQL Global Development Group and has been leading a contributor to the development of PostgreSQL since the early days of the project. He's also an author of PostgreSQL. Introduction Concepts is the name of that particular book, which he authored, and is also widely regarded as a definitive guide to PostgreSQL. Bruce has also contributed to many other books and articles on PostgreSQL, and he's a frequent speaker at conferences and events around the world. His expertise and insights have helped to shape the development of PostgreSQL into one of the most advanced and powerful database management systems available today. Today, Bruce is sharing his knowledge on Postgres Optimizer with us. His insights and perspectives will undoubtedly provide valuable learning opportunities for all of us. Before we get started, I would like to review a couple of housekeeping items. First off, this presentation is being recorded, and we will share the recording along with the slides before the broadcast. So please keep an eye out of that email this week. Second, please note that the lines are currently muted. We expect the presentation to last most of our time today. We'll keep taking questions, so please be sure to enter your questions into Q&A. If we can get to your questions, we'll follow up after the webinar. Please note that if you ask a question as an anonymous attendee, we will be unable to attend follow-up things, and we will be sending or answering your questions if those are not covered during the session after the session. With that, I will hand it off to Bruce to kick off this particular webinar session. Bruce?
Thanks, everybody. Great to be speaking to you today. Obviously, we're all sort of pulling out of the COVID lockdown, and we're having this opportunity to cover what I think is a pretty fundamental topic. I've been traveling quite a bit. I have events still in the next couple months in Malta, Amsterdam, Cleveland, Chicago, and Denver. Things are heating up. We have a lot of great events around the world. So feel free if you're near any of those places to look that up. This presentation is actually one of 60 presentations that I have on my website. My website is right down here to the left. So if you're interested in looking at these slides or recordings of these slides or any of the other 59 presentations, feel free to look there. In fact, this is actually a two-part webinar. We have another webinar next Monday at the same time, where we're going to be talking sort of as a follow-on to this presentation called Beyond Joins and Indexes. And I think that's going to be really interesting. This gives you the basics of the optimizer, and I think the most fundamental value and the most fundamental issues with the optimizer. In the next talk next week, we'll really cover some of the other things that we do related to parallelism, related to complex group by processing and so forth. So feel free to also reserve your spot for that webinar as well. Again, this is kind of a two-parter. That webinar actually even references a new presentation I did on partitioning. There'll be a link next week actually to those slides. So if you're curious about partitioning, make sure you come next week as well, because there'll just be a link at the bottom of one of the slides. Slides aren't even published yet. I'll be delivering those in Malta. But the link will be in the next set of slides, and you can sort of preview them if you're curious. But for today, we're going to talk about the basics of the optimizer. The optimizer is actually the thing that got me involved with Postgres, the thing that excited me about the code and digging into how Postgres works. Obviously, you can see from this diagram, most application code really sends results to this blue box on the right, which is the database, the Postgres database server. And rather than being one monolithic piece, it's actually made up of a variety of pieces. I've kind of recreated the blue box here. And in fact, the next slide even blows up that blue box. And here's where we actually start talking about the actual query processing in Postgres. In particular, we're going to talk about what the optimizer does. So we're looking at the top left. We start by parsing the SQL. And then we go to a traffic cop section, which identifies whether this is a query that needs to be optimized and executed or merely a utility command. If it's one of those optimize execute type of queries, meaning it's a select, an insert, an update, a delete, or a merge, which is new in Postgres 15, it goes and runs what we consider to be the traditional query optimization and execution. It goes into something called the rewriter, which handles things like views and rules. And then the next two blue boxes represent the optimizer. The optimizer effectively generates a number of paths, a number of possible ways of executing the query. And then once it chooses the cheapest path, it generates something called a plan. And as you can see here, the plan comes out of that second optimizer box right here and is fed into the executor where we execute the plan. I do have an internals talk which goes into more detail about this, but in general, this is how the system works and how the flow of the query kind of operates. But as I said before, this is really where I got interested in Postgres. I was in 1996 when I started. I was an application developer. I was using Ingress and Informix at that time. And I would send these English language queries, SQL, to the database, and somehow the database would figure out how to execute it and return a result. And I always was fascinated. How does it do that? How does it know what the SQL means? How does it know which indexes to use? How does it know what join method to use? And obviously with Ingress and Informix, I couldn't see the code of how it was done. But with Postgres, I could. And that's actually the thing that attracted me to sort of get involved initially, was just really curiosity. How does Postgres work and what makes it work? And that's what we're going to kind of go through a little bit in this presentation. So there are three decisions the optimizer has to make: scan method, join method, and join order. Now, those might not mean a lot to you, but in this presentation, we're going to go through all three of those sections and explain exactly what they mean. So scan method, let's talk about that one first. There are actually three different scan methods that we support. We support something called a sequential scan, a bitmap index scan, which I'll explain in a minute because that sounds really complicated. And then also something called an index scan. But before we go into that, I'm going to set up some of the basics. Okay. So what we're going to do is we're going to use the Postgres system tables as our data source, because everyone has the system tables. They're already populated. All we want to do is illustrate the optimizer. So let's use the system tables themselves to illustrate that. So here is the output of the first 8 rows of the PG class table. The PG class table is effectively the table that represents all the system tables. So these are the first 8 rows of that. And what we're going to do is we're going to slice off the first letter of the system table name. Okay, because remember, these first ones three start with underscore, the second 3 start with A, and then the CC, and that's what we're doing. We're just slicing off everything but the first letter. Okay, that's going to be our data source, is the first letter of all the system table names. Then we're going to create a temporary table, and we're going to randomly add these letters, row letters, to this sample table. And then we're going to put a bunch of junk at the end, like X's, just random X's with this repeat command. And we're doing this so that the row has a little heft. It's not a really short row. It's kind of hefty. It's got 254 bytes, I guess, or so in there. And then we're also going to add them in random order. That order by random actually will generate them in random order, and they won't all be in order. They'll be randomly in the table, which actually does affect the optimizer. I'll show you that as well. And then finally, we're going to create an index. All right. Now, you might want to try what I'm doing on your own server, and you're welcome to do that. If you take a look at the bottom, the URL there at the bottom is indeed all of the content that you're going to see in this webinar is in that SQL file. So if you download that SQL file, or if you download these slides and click on the blue text, it'll automatically open your browser, and your browser will download the SQL file, and you just pipe it into PSQL. The whole presentation will just fly right in front of you. So feel free to do that. Maybe you don't want to do it while I'm talking, but maybe you do. But take a look at it if you want to actually try what I'm doing and actually play with the data a little bit and see exactly what I'm doing. Often that's a better way of learning, is to try it yourself and then try some queries and see what results you get, and then change something and try it again. That's actually how I wrote this presentation. I wrote a whole bunch of SQL. I ran it, I captured the output, and then I pasted it into my my document editor, and then added colors and added formatting and so forth. That's actually, I probably have 7 or 8, 9 presentations that are all that way, that they're just really SQL files that have been crafted and then run and then captured and made into a presentation. I'm going to add a function called lookup letter. This has to be done so that I can do some of the examples a little better. Again, it's just looking up a letter in the query, in the table, from the sample table. You can see from sample. So let's take a look. What's the distribution of the sample table here? I'm using a common table expression. If you're not familiar with common table expressions, I do have a presentation on my website about that, how they work. But this is just basically a simple common table expression, which is basically analyzing what type of data distribution I have in my table. And this is my data distribution. This is my sample table. So effectively, I have 78% of my rows are P, okay? 3.6% are S, 3.2% are C, 2.8% are R, and then all the way at the bottom, I and K, there's one of those, and it's 0.4%, okay? So one of the things I'm going to highlight here is that the optimizer knows how common some of these things are if you give it the right information, and with that information, it will actually generate much better queries for you. So let's take a look at, is that actually true? So here we're going to do a set on the letter P. We're going to say, tell me how many P's there are, and we're going to use explain. And the first thing that triggers is that index scan, which I mentioned before. Okay, an index scan, and P is a very common letter. Okay, so for a P, a very common letter, we have an index scan. Now let's try another letter, a D. Now the D is not as common. It's kind of in the middle somewhere. And we have still an index scan. And we have the K. Now you may remember before I told you the K is the least common letter. All right. And we get an index scan. So what is going on? I'm going to back up a little bit. I did the P. We know the most common letter. I did the D in the middle. I did the K. All of these are generating an index scan. It does not appear the optimizer is doing what we need it to do, because it isn't distinguishing between very common values and the least common value in a query. Why is that? Analyze. Okay. So there is a command called analyze, which gathers statistics on your tables. Okay. In this particular example, I have to call the command analyze so that the system knows, the optimizer knows, that P is a common value and that K is a rare value. Okay. In this particular case, without running analyze, this optimizer does not know that. Okay. Why is it necessary for this particular case? Is, you may remember before, the sample table is a temporary table. So what I've described here at the bottom in this text, okay, is that temporary tables, normal tables will automatically get analyzed statistics within 1 minute of there being any rows in the table. As soon as you create the table and put some data in there, auto vacuum on a non-temporary table will automatically run and get you statistics. Now, if you need to run a query from the time you load the table to the first minute or two, you may still want to run analyze manually because you may not have the minute to wait for analyze to run. But most tables, yeah, you load them and they sit idle for a couple minutes and then analyze runs and then you run your queries on them. Works perfectly fine. But if you're running a query right away on data that's freshly loaded, you should probably be running analyze manually. And then also, if you're doing operations on temporary tables where auto vacuum cannot actually run on those, then you should be running analyze. So in most cases, you never probably have heard of analyze because you don't need it because you're probably letting auto vacuum handle all. I know it's called auto vacuum, but it does analyze as well. I know it's a poor name. I guess we could have called it auto vac analyze or something funny like that, but we call it auto vacuum. But it does analyze as well. And effectively, that's why you probably don't have to do this yourself, but that's why I had to do it. So as soon as I run analyze, notice the P switches to sequential scan, which is what we would expect from a very common value. Okay. And this is what a sequential scan looks like, just a straight scan, straight through from start to finish. The very common value, it's not worth accessing the index. It's not worth even a bitmap heap scan. Normally, indexes have to be very selective, almost, I would say, under 5% of the rows, and sometimes under 4 or 3% of the rows until an index lookup is actually useful. Because remember, an index lookup is going to do a lot of random IO. It's got to read all those index pages to get to the heap. Because the P is so popular, easier to just read the heap, forget reading the index completely. The D actually generates a bitmap index scan, which is that, remember, it's that middle value. It's not rare, but it's not common. And what a bitmap index scan does is it basically creates a bitmap of all the matches from the index and then uses that to access the heap. So values that are not rare but not common often end up in this bitmap heap scan option. And then finally, the K, which there's only one of, and we know that. In fact, if you've been looking, this literally says 1. It knows there's one of these rows. And if we back up, it knows there's 4 of the Ds. And if we back up again, it knows there's 199 of the Ps. That almost exactly matches what we saw on previous slides. So once we ran this analyze command, the optimizer had a very, very good idea of how accurate they were. Okay, 99, 4, and 1. It knows, and it's using that information to properly execute the most efficient way of accessing. Okay, and this is the way an index scan works, particularly for B tree. It's reading a bunch of levels until it gets to the right row. So let's put this together. Let's look at all the values and their effects. So what I've done is I've created a common table expression at the top again, right, where we loop through, and then I'm calling that function called lookup letter, which kind of gives me a view. And you can see here all the P's are sequential scans, and as we are still at 9 rows, 8 rows, and 7 rows, there's still sequential scans. Okay. And this is an even better query that actually limits, so we only see one line. Is a little trickier, so we can see it all on one screen. And this to me is this is the screen. This is the slide for this presentation. What it's showing you in red is that all of the common values, as it considers common, are doing sequential scans. All of the middle frequency values are doing bitmap heap scans, and all of the rare values at the bottom in magenta are doing index scans. Okay. And this is exactly what you would like to see from your optimizer. The concept that it's taking care of the frequency of your values and automatically tailoring the right access method. And frankly, this is the reason relational systems are so popular. And this is the reason relational systems continue to become popular from now and into the future. Because we've all heard about NoSQL systems, we've all heard about very quick access systems. But as soon as you go for very fast access, and I'm not trying to belittle those systems, but if you need more than a very simple data model, the smarts of trying to choose whether to use an index or not in your application is incredibly difficult, let alone the complexity of choosing a join method, which I'm going to talk about in a minute. Okay. So the point is that the reason relational systems are popular is because they take all of the guesswork out of what method should I use, what join method should I use, and it pushes it all into a central database that has statistics, that knows how common the values are, and can adjust based on if you all of a sudden a new letter becomes common tomorrow, the optimizer automatically will adjust to that. Okay. Trying to take all that smarts and put it into an application, to remove it from the database layer and bring it into is just incredibly difficult. Again, unless you have a very simple data model and you need absolutely the fastest speed possible. But a lot of times organizations will optimize for that very fast speed, but then down the road, as their data model becomes more complicated, as their data structures change, as the frequency of their queries change, all of a sudden their application doesn't know that. It becomes very unwieldy, very slow. Application has to become very pop because you end up re-implementing the optimizer inside the application unless you have this smarts in the data layer itself. Okay. I know it's a little bit of soapbox, but I can't overestimate enough. This looks great and these colors look great, but this is the beauty of a relational system with an optimizer. It takes these problems away from the application and it puts them in a dynamic layer that can automatically adjust even as the underlying data changes and the frequency of that data changes. And of course, for ad hoc queries, for analysis, for new applications, all that stuff comes with it. Very hard to do this without having it in the data layer itself. So let's suppose we want to like break the system. Let's suppose we want to turn off sequential scan and we want to turn off bitmap scan and we want everything to use an index. So what I've done here in red is I've turned off these other two optimization layers, optimization options. And so it's going to force it to use an index scan. And I'm going to run the same query. And what we get here is effectively all index scans. So as you may see here, the cost of these queries is now from 39 all the way down to 8. If I was to look at, if you remember the previous slide, it was 13 to 8. So look at this P here. This is what we used to have. For a sequential scan, the cost is 13. As soon as we forced an index scan is at 39. Now these numbers are perhaps wrong. Maybe there's something wrong about them. Run and test it yourself. Turn off some options. Do a timing on the query. Log min duration statement or log statement, log duration. You can see how long these queries are taking. And you'll find out pretty quickly. The optimizer does things not perfectly, but probably 98% of the time, it guesses correctly which time to switch between one or the other. And if it's wrong, it's often wrong within 5% execution time. So it may be true that it isn't absolutely correct for every query, and it certainly isn't for every query. But for the majority of queries, vast majority of queries, it actually runs very, very well, and certainly better than an application could try and do it, unless it had perfect knowledge of the data, not only data today, but the data in the future. So again, kind of interesting to turn it off and see what it is when we shut it off, and then see what we actually get. So let's go to the next section. I talked about access methods. We've covered those. I showed you the colors. I explained how the optimizer figures that out. let's talk about join methods. There are actually 3 or 4 different join methods. I'm always on the fence about this. There's 2 type of nested loops. There's a nested loop with an index scan. There's a nested loop with a sequential scan, and then there's hash join and merge join. And I'm going to illustrate these. Again, this is the second decision the optimizer has to make. Remember, the first decision I had to make was access method, right? How is it going to get to the data? Second decision is join method. Third decision is join order. Okay. So basically we have a nested loop, 2 types, hash join and merge join, and we're gonna dive into these right now. Now, to dive into these, we're gonna have to join things together, so we have to create another temporary table. In this case, I'm going to pull my rows from pgproc, another system table in Postgres, again, a bunch of numbers. So I'm going to create a sample 1, which is numbers from pgproc, and I'm going to say sample 2, which a bunch of numbers from PG class. Okay, so 2 temporary tables. And again, these tables have no indexes and there's no optimizer statistics. Okay, so these are the raw tables. Remember, auto vacuum can't see these because they're temporary tables. Okay, and we have no indexes. And what we're going to do when they're in random, and then what we're going to do is we're going to run this again. We're going to add some a little later. We're going to add some statistics, and then we're going to add some indexes, and we'll see how things change. Okay, so let's just kind of walk through a very simple example. So here I'm joining 2 tables with a tight restriction. So I'm saying join sample 1 to sample 2 and make sample 1 equal to 33. So what actually happens is that it runs sample 1, okay, and it puts it on the outer side of the query. And then for all of the values that equal 33, it then checks the inner side. And this is the diagram of that. Now, the outer side is what we call the driving side, the side that really initiates the join, and the inner side is the receiving side. So what happens in this query is we're running through the outer side. We're looking for 33. And once we hit every 33, we then look at the inner side and we compare that 33 to every row on the inner side. Okay. Now, this is a very simplified join method. It really is only good for small tables, and it has no setup required. So it's very easy to create and just do really quickly. But again, any sizable data set, I wouldn't recommend this for, and the optimizer wouldn't naturally choose this for any sizable data set. But of course, the optimizer has no idea how big the table is because we have no statistics on it because it's a temporary table, right? And we haven't run analyze yet. So that's why we're getting an inner index scan, even though these are somewhat sizable tables. And this is what the pseudocode for a sequential scan looks up in Perl, basically. Is that Perl? Yeah, whatever. It's in C. So this is the next one where we're actually using a looser restriction. We're saying greater than 33. So now for the outer side, we're actually doing a much larger range. So now instead of a nested loop, we're choosing a hash join. So you can see down here that sample 2 is hashed, okay, for all the values greater than 33. And then we run through and do a join from sample 1 to all the rows in sample 2. Okay. And that looks like this. We're effectively taking the inner side and we're creating an in-memory hash. Okay. And then from the outer side, we're going to join to that in-memory hash, basically. Okay. So that's how we basically do the join. Hash sits in memory, and we're just basically doing very fast lookups. Now, instead of doing a sequential scan on the inner side, which is what we had to do for nested loop, we're now doing very fast lookups into the hash. And this is what the pseudocode for that would look like. Okay. Now, if we want to join 2 tables with no restrictions, here we're just saying sample 1, sample 2. Now, this is a much bigger join, and we then use something called a merge join. So in a merge join, you can see we're actually sorting this sample 2, and we're sorting sample 1, and then we're going to merge them together. And that looks like this. We basically sort the left-hand side, we sort the right-hand side, okay? And then once we've done that, we can basically compare the first row to the first row. If it matches, we can advance from the first row to the second row. If that doesn't match, we know all of the rows are higher than that. There are no more matches. So now we can start with the second row and compare a match, no match. Okay, we can stop. Now we can start with this one and continue on. So we're basically going lockstep through the table. And we're only having to really scan once on the outer side, but we have to, and kind of once on the inner side, because again, we don't have to back up because we know nothing earlier could match and nothing later could match as long as we have equal values. Okay. And again, this is ideal for large tables, but the downside is that you have to sort everything, right? So everything has to be ordered, and that's expensive, but again, that's a great way of going at it for large tables. You can imagine trying to do a nested loop on two large tables. Forget it, right? Like 1 million rows joined to 1 million rows would be a trillion comparisons, right? That's not going to be fast. Okay. This is the pseudocode for a merge join. So order of joined relations is insignificant. If we actually swap join sample 1 and sample 2, it still does everything the same way. So Postgres is a cost-based optimizer. Doesn't matter what order you put things in, it's going to do the same thing. Now we're going to go to our next stage. We're going to add optimizer statistics, right? So remember, up until now, we didn't have statistics, a temporary table. We hadn't run analyze. Auto vacuum can't see it. Now we're going to add statistics. And as soon as we do that, this query, which used to be a merge join because it didn't know how big they are, has become a hash join, right? Because now it knows exactly how many rows. It knows there's 260 rows in sample 2 and 2,256 rows in sample 1. Okay. And it's going to hash the smaller of the two, which is sample 2. That makes sense. Remember, the hash has to fit in memory. So let's use the smaller one, and then we'll do the lookups from the larger. Right outer join. If you're familiar with outer joins, we actually have the ability to do what we call a hash left join. So when a hash lookup fails to match, we still return the row. So again, just because you're using an outer join, we can still use hash joins. We have a special hash left join or right join for this particular case. Cross join, you may not even know this is part of the SQL standard, but cross join basically says compare every row to every other row. This one has to be a nested loop, right? Because almost by definition, that's what it is. You're asking it literally to compare every row to every other row, and you will get a nested loop in every case because it would make no sense to choose any other option. Now we're going to create 2 indexes on these tables, and we're going to see how the optimizer choices change now that it has statistics, which we created earlier, and indexes. So this one, remember, equals 33, used to be a nested loop sequential scan. Now it's a nested loop index scan. We're actually using the index 2 indexes. We're using the index on the outer side to find the 33. And then we're using index on the inner side to find matches in sample 2. Okay. Remember, this originally was a nested loop of 2 sequential scans, incredibly slow. Actually, now it's become very fast. That's fantastic. And again, it's a very narrow query, only equals 33. We can look it up really fast on the outer side, and then we can use the index to look up really fast on the inner side. That is an ideal query plan to use for that query. In a nested loop with inner index scan, as you can see, the lookups are happening. The lookups on the inner side are not happening with the sequential scan, but now are a index scan, which obviously is much faster. Again, assuming an index has already been created for this inner table. And this is the pseudocode for that. Query restrictions can affect the join order. So for example, even if I'm restricting on a non-joined column, I can still get, it still affects the query plan. So you may remember way, way, way back, I talked about the fact that I made the row a little wider, right? And you may remember I did repeat X. So they were all X's in this junk column. But what I'm querying here is I'm saying, don't give me X's, only give me the ones that are A's. Now the optimizer knows that there are a lot of X's in that junk column. It doesn't think there are any A's, but of course somebody might have inserted them in the last minute or since the last time auto vacuum ran. So it's going to give me the benefit of the doubt. It's going to say, I don't think there are any A's, but I'm going to assume there's one, right? And I'm going to run my query. I'm going to choose my query plan on the assumption that there's really only one or a tiny number of A's. And what's happening here is it's choosing a nested loop with a sequential scan. It doesn't have an index to look up, okay? But it does have an index to use for the inner side because we're still joining on the ID column, right? So it can't use an index on the outer side because we haven't created an index on junk, but it can do that on the inner side, and it still uses that. Contrast that with this query where I'm looking for X's. Now the system knows there's a lot of X's, and that we've gone from a nested loop now to a hash join. Again, we're doing, a sequential scan on the outer side, and then we're hashing the inner side and pulling all of the X's, and they're all actually X's anyway. But you kind of get the idea. We're filtering as we load the hash. This is actually very creative the way it's doing it. We're saying we're gonna have to load, you have to do a sequential scan to load the hash anyway. Let's filter out anything that isn't XXX. And that way we won't have to worry about this anymore. And again, very nicely done. And again, also very convenient that the XXX was on the inner side. So it was on, it was on the inner side, the side where we can filter out the joins, and it's the small side. Remember, the small table usually is the one we hash. One final thing I want to talk about is the limit clause. The limit clause actually is kind of non-standard, although most relational systems now support it in some manner. The limit clause allows us to limit how many rows we return. And this is a much better way of doing a query than using a cursor and saying fetch 1 row or fetch 10 rows. Putting the limit in the query itself actually helps the optimizer to plan the query. So for example, we're back in this query where we have our sample 1, sample 2 join, and we're using a hash join here because that's what it wants to do. But as soon as we add an order by, notice that we switch from a hash join to a nested loop. Now, why did we do that? We did that because the system knows that we're only returning 1 row. We're not joining really both tables together. We just need the lowest value in the row to match the lowest value in the next row. So we only have to do a couple joins. That's the assumption with a limit 1. So it's going to use a nested loop. Remember, no setup cost. It's just going to try it really fast and return that 1 row as quick as possible. Even when we do at limit 10, it still thinks that the nested loop is faster. But once we get to a limit 100, we fall back to the hash join because it now realizes that there really isn't a good way of executing this except through, a full hash join. Because trying to get the 100 earliest rows is probably going to be too slow. Let's run the whole query. Let's hash the one side. Let's join it and then return the 100 rows that the person wants. So what this highlights is that the limit clause even affects how the queries turned out. So that is all I wanted to cover today. I'm thankful that you were here, and hopefully it was a blessing to you to hear how this works. I picked this picture just because I kind of think of it how the water is sort of the plans that come down, and depending on what rocks it hits, it chooses a different plan. And the water efficiently, if you ever done fluid dynamics, it efficiently runs down the stream in the easiest way possible. And I think that's the goal, I think, of our optimizer, is sort of to have that sort of continuous flow like that. Again, next week we have sort of, I would say, the follow on to this, much more complicated because it covers 42 other things the optimizer can do and choose for queries. And I think that'll be also a really interesting presentation as well. So back to you, Vibor.
All right. Thank you, Bruce. It was a great session. A lot of information around the statistics, different kind of scans which we support in PostgreSQL, right? So yeah, all are very good information. There are a lot of good questions were asked during the session also. I answered 5 of those, but there are some more questions which are waiting for your response. First question is from Keshav Panthi. He's asking the question around statistics, especially analyze, I believe. Question is the statistics gathered, analyzed automatically by the PostgreSQL server? If yes, how is it scheduled? Then follow-up question is, what is the recommended approach to maintain the up-to-date statistics when there is a huge ad hoc load done on a table? Does the create statistics create a lock on the table when it is running? So it's like there are 3 different questions.
Yeah, great questions. You're right. I didn't cover it. I didn't want to cover too much material, but it's great you asked that question. So Postgres has an auto vacuum process. So if you look in the Postgres documentation, it's going to explain that the auto vacuum process does cleanup of old rows, but it also does auto analyze. So internally, the way it works is that when a table's when tables rows change, I think roughly 10%, the auto vacuum will automatically update the statistics for you. So you basically have the ability, it automatically, as your data is changing, it's automatically going to be updating those statistics. And that's why you probably never had to care about it, because in most cases it happens just fine. You can do a couple things that give it a little help. I have a blog entry. I know I have 600 or so blog entries on my website, but one of them is basically talking about making the auto analyze more aggressive. One of the tricks I actually do, I recommended in that blog, is to basically say, there is a setting in Postgres which will make the auto analyze more aggressive. So I remember I said 10%, maybe you want to make it 5%, but maybe you don't want to make it 5% during the day. Maybe during a quiet time, maybe you want to lower the thresholds for auto analyze, maybe in half, and then reset it once you get busy again, right? So the idea is that you would have more aggressive analyzing during times when you're not busy, and then that would make it less likely that analyze would run when you are busy, and also give you more accurate statistics. So that's kind of an interesting way of setting things up. The good news is that even if you don't touch that, the auto analyze is a very lightweight system. It basically randomly samples a number of rows and gets very good statistics using very few block reads. It does not lock the table at all to do that. It's basically just going to randomly check a bunch of pages in the table and then generate statistics that are representative of the full table. Are they ever going to be completely accurate? No. Does it matter? No, because the whole process of the optimizer is going to be imperfect. The goal of the optimizer is to get a number that's close enough to be accurate. And most optimizer choices are very easy to make. It doesn't matter whether the statistics are absolutely on or off by a certain percentage. In most cases, even if it chooses a poor plan, it'll be within 5% execution time of an ideal plan. Because the data is changing all the time. You're never going to get perfection here, but the optimizer does a very, very good job. And again, if you want to make it more aggressive, I do recommend that blog entry where you can kind of make it more aggressive, maybe during non-busy times. And you can also modify the cleanup process, auto vacuum, the vacuum part of auto vacuum and the analyze part of auto vacuum. You can both of those, you can make them more aggressive during non-busy times and then less aggressive. But in both cases, there's no locking that occurs in either one.
Right. And the create statistics command takes access share lock, right?
The create statistics command, I didn't even get into that. The create statistics command is designed to get correlated statistics between multiple columns in a single table. So for example, if you have zip code and city, they're very correlated, right? And if you have queries that are querying both of them, and maybe the optimizer is not understanding, it has statistics for one column and not the other, but doesn't understand how they're related. Create statistics creates cross column statistics, which can be incredibly helpful. The creation of those statistics themselves is going to have to lock the table, because you're modifying, sort of a very lightweight lock on the table to basically put the statistics in place. But going forward, the updating that statistics is going to happen by auto vacuum, or by analyze manually. And again, there's no locking occurs while those are being updated.
Correct. Yeah. And then there is one anonymous, I think it's based on one of your slides. I'm not sure which slide is that. I can see the count of E as 2, but in the lookup letter, it is showing rows as 1. Why is that?
Okay. So,
I think this one, I believe.
well, this has width of 2, but
Oh, it's a bit
that's,
2.
width of 2, row 1. I'm looking for a rows of 2. Let me see here. I need to know what slide, I'm afraid,
Yeah, the
on that
lookup
one.
letter, you have done that, right? So,
Yeah, I mean, I think you can just download the SQL and see what numbers you get. These are gonna be not absolutely the same all the time, because it randomly samples the table. So the actual numbers could be a little off.
correct.
I happen to have hit pretty accurate numbers here, but the
Mhm.
numbers could be plus or minus a percentage, and it wouldn't matter to the system. It would be very normal for that to happen.
Right. Other question is from Lauritz. I hope I'm pronouncing the name correctly. Does anything similar happen to what you said about needing to analyze the temporary tables, also with materialized views? So, like, we recommend to run the analyze command on temporary tables, right?
Yeah.
Is question, do we need to run command for materialized views too?
No, materialized views are really, I know that it sounds funny, but they're actually tables to us. So they're actually stored in the system. They're shared, which means they're not local, they're not temporary. So Analyze is going to run through those just fine. When you refresh that materialized view, again, if 10% of that table changes, then auto vacuum will automatically come and analyze that for you. So yeah, it's not like it would be different if we had something like virtual tables. Like views are not analyzed, because a view doesn't store any data. It's just a structure, right? But a materialized view is by definition materialized in memory, in on disk. And those appear as normal tables, even though there's a query behind them that we use to refresh it.
Right. I mean, you can run analyze command, as you mentioned that you can tune auto vacuum to do that kind of activity for your materialized views. So yeah. Then there's another question. Are there guidelines for the amount of tables statistics that should be kept per table with respect to the number of rows in a table?
So there's a statistics target, which I think is 100. So we remember the 100 most common values in a column, and
Hmm.
we also remember the like a histogram of 100 slices for the distribution. We also calculate statistics on if you create an index of an expression, we're going to create statistics on that too. So a lot of people don't know that. I have a separate indexing talk that talks about that. But when you create an index on an expression, we will get statistics on that expression as well. In terms of like guidelines, if if for example you have let's suppose you have a table and you have 150 very common values, and like the rest of them are unique, you might want to set the statistics target to be 200 maybe for that column, right?
Mhm.
because then we would capture all 150 common values, and then everything else we know is unique. It's kind of hard to know exactly what to recommend. The size of the table, I'm not sure that's really a measure I would look at. We're really looking for the only case I think we really where the statistics target starts to fall down is when you have columns that have very ununiform distributions. Like if a column only has 5 distinct values, no problem. If a column has all unique values, no problem. The case I remember is a problem is you got like 150 very common values, and then everything else is unique, and you only are capturing the first 100 or the most common 100. That last 50 could potentially give you suboptimal output, plans. Anything else before that? That's how I would recommend it.
Yeah, and the default statistics target, which we have 200, is optimal for most of the cases. In some cases, let's say if you have a kind of a data distribution, a table not very optimal, then people generally go to the 150 or 200. But as soon as you increase this default statistics target value to higher, you also increase the impact on the performance of the index scan or disk IO2. So
Yeah.
that's why you have to be very mindful about which value you want to use for your default statistics target. I think I've already explained very well, Bruce. So
Yeah, you're right. I've seen people set it to like 1,000
yeah, becomes
and
crazy.
without testing the impact of it. And the problem is not so much the sequential scan. The problem is now the optimizer has a lot more rows to go through
Mhm.
to identify how common this value is. And again, on columns where this is not really giving us much usefulness, it's just going to slow down the system.
Correct. Yeah. All right. So there is one more question, and we will take this as a last question. Remaining question will respond via email because we have limited time. This is the last question which we are taking as a live answer. For live answer, if there is a column on a table that at least seems ideal for bitmap index scan, let's say 4 to 6 distinct values with no nulls for 1,000 plus and 10,000 plus of rows. There is no way to explicitly create a bitmap index. So what is the best practices in Postgres for this case? So the person is actually asking for the bitmap indexes. We don't have a bitmap indexes. We do have B-tree indexes, right? And if there is a use case of the bitmap index scan, how Postgres would help, or what are the best practices around it?
Yeah, that's an interesting one. So you have a lot of duplicates
Mhm.
in a column. So I have two really recommendations there, and I'm gonna go a little differently. So you're focusing on the bitmap aspect of Postgres, but in fact, let's back up a little bit and let's talk about index types, right? So one of the nice things about Postgres 14, I'm not sure what version of Postgres you're using, but we've become much more efficient at storing duplicate values in B-tree. Postgres 14's made some big improvements. I think Postgres 15 made a couple minor ones. So
Mhm.
if you're indexing a column like that, you might want to make sure you're running a newer version of Postgres because B-tree would be better. Another way of going at it is to not use B-tree at all, because the GIN index type is designed to handle duplicates very efficiently. Now you normally hear GIN for something like JSON or full text search, but it would handle that. It would handle that just fine. There's also a contrib module called B-tree Gin, which is a Gin version of B-tree, which again is another way of sort of indexing rows with very common values. Um, so you're absolutely right that you can't create an on disk bitmap. In fact, our to-do list says we're not interested in implementing that feature. And the reason is because on bit on disk bitmaps are very hard to update. They're very good for data warehouse if you're doing a single load and then never touching the data. But we don't assume that's the case here. We assume we're a live OLTP system where you're also doing data warehouse. And for that reason, we don't have on disk bitmap, but we do have B-tree, which stores the duplicates very efficiently, but Gin, which would do a much better job. But then you also get into the thing that I talked about earlier, where an index lookup really doesn't make a lot of sense unless a value is very unique or nearly unique within a table, right? So you saw what happened with the p value, which it didn't use sequential scan, but we had to get very far down. I think it was the S or the C, where it started using a bitmap scan, pulling entries out of the index and then looking them up in the heap. We find that to be probably a better solution than than an on-disk bitmap. But maybe an even better solution to that would be to switch to something like Gin, which could store the duplicates very efficiently. Now, if again, if those values still represent 10, 15, 20% of the table, I wonder whether we're still going to use an index at all, because index access is very expensive, even on SSDs where random page cost is near the same as sequential. That index access is going to be costly, and we're just often going to end up just sequential scanning it through. Another option you can do, and I have an indexing talk on my website about this, is to create like an expression index. So you can create an index that just represents all the values of a certain code. Like, if ABC is a code in your table, you can just create an index that just has ABC entries, right? And it'll just pull straight from the index. And there's a lot you can do. Partial indexes. There's a whole bunch of cool things you can do with index alignment and sort of crafting. You might want to look at my my indexing talk. It's on my website under extended, and it's called Flexible Indexing with Postgres.
Nice. Thank you, Bruce. Yeah, there's a lot of questions here, and I can see how people are curious and they want to know more about this topic. We will cover all the remaining questions via email. We will respond to you after this webinar session. We will send you a recording, a link, plus answers of the questions, and that's it. So thank you so much. Thank you, everyone. Thank you, Bruce. So yeah, thank you.
Great. Bye-bye.
Bye.